therefore a lot of water will not get out. You cannot get some of it out. I'll talk about that in a minute. Various reasons as well. So that's what it is. Okay, simply the volume of the void space over the volume of the entire material, and expressed as a percentage. So something is 30%, 40%, 50% porosity. Put a little asterisk up here because we'll encounter a term later on called effective porosity. This is a measure of the void space through which the water can actually travel or be extracted from. Okay, so connected pores, all sorts of things like that. Okay, so it's a measure of the connectedness of the pores, and it gets rid of water bound in clays, okay, water that's sealed up in bugs and vesicles that can't be got out. Okay, so it's a much smaller value than the total porosity. So no matter how porous your rock is, if all those pores are interconnected, you fill it with water, you never get all that water out. Okay, you can't. So effective porosity is that particular parameter. Two forms of porosity, I've alluded to already. Primary porosity, the original pore space created during the formation of the rock, so the pores in between grains of sand as they liquefy to become rock. Okay, that essentially is what we're talking about with primary porosity. It's generally the dominant form in our plastic sedimentary rocks, as you'd expect. Okay, the clasts are all just piling up, cementing together, leaving the holes in between them for the water to be stored in or to get into or be taken out of later on. And it's controlled by the grain size. Larger grains, better porosity, generally, as long as there's lots of void space. Okay, it's really good. Grain shape, rounded grains, better porosity. Okay, they stack nice and efficiently. Okay, you don't get little angles filling in holes. Okay, the sorting, the better sorting, the better porosity. So for a really good aquifer, you want large grains, rounded grains, well sorted, so all the same size. That'll give you a great aquifer. Okay, it doesn't always happen that way. Cementation, less cement, get porosity, not filling up those void spaces of material that's taking the place of the water. Secondary porosity, pore space formed through fracturing and weathering of the rock after its formation. So you get secondary porosity in all rock types, right? It's generally much more important than the crystalline rocks, igneous rocks, metamorphic rocks, okay? Because they don't have much or any pore space when they are formed, okay? Just because of the nature of how they form, especially the metamorphics. It dominates the non-plastic sedimentary and non-sedimentary rocks. So this is controlled by the degree of weathering, okay? How much weathering has occurred in there to open up void space, open up fractures or whatever that happen to be there. The extent or the persistence of the fractures, whether they extend deep down the ground or they extend a long way laterally. Okay? If you haven't got that persistence, you haven't got much space. The spacing, lots of closely spaced fractures, much better than a few widely spaced fractures unless they're really gigantic. Openness, the aperture, right? So with the 20 millimetre things, whether they're tight, okay? The fractures could be tight, but they're there, lots of them, but they can't hold anything if they're closed. And whether they are filled with anything, okay? So we have mineralisation, okay, that had come along and started to fill or totally filled in fractures after they have been created. And the overall fracture pattern as well, whether you've just got a 2D pattern or a 3D pattern, where the fractures are connected all the way through the rocks and we can percolate all the way through, and you can access them all the way through, etc. So there's a whole lot of controls on these things as well. Examples of primary porosity, here you go, well sorted. You can see we've got grains that are pretty much all the same size. You get large void spaces because you don't get little tiny grains sitting in here filling up those voids. You've opened up a lot of space for your aquifer to be able to hold water. See, when you get a poorly sorted one, you've drastically reduced that porosity because little tiny grains, okay, get in here and fill up those nice spaces. Okay? All these well sorted ones packed together nicely, leaving big void spaces. You can see how the rounding makes the void spaces even bigger. They're not angular, so they don't protrude into the void space, into the porosity there at all. Well sorted here, and porous grains. Okay, so you've almost got double primary porosity. You've got porous material which holds water, and the gaps in between it also form nice big pore spaces that hold lots of water as well. And of course, these are really crappy ones. Well sorted but cemented. The cement, of course, displaces all that porosity. It fills in the space, water can't get in. So you haven't got a very good aquifer material there at all. Secondary porosity, same sort of thing. Always formed through solution, okay? Especially prevalent with limestones, of course. Okay? Water percolating through. The limestones are quite soluble. Leave behind large, potentially large pore spaces. Anyway, cave systems, okay, really good examples. But you're going to get a lot of planar voids forming and things as well through solution. typically in limestones, okay, because like I say, they're easily soluble. Fractures in crystalline rocks, another one. This is a really important source of water, and we're talking about this a reasonable amount in future lectures because there's a lot of this taking waters from fractured rock going on in New Zealand. Depends, as I said before, on the persistence of the fractures, their openness, whether they've been infilled or whatever, their interconnectedness, okay, but it's a really important source of water, natural source. There are fractures in granite, fractures in ignimbrites, basalts, any of those things, okay, even basalts have a lot of fracturing, don't they? They have cooling fractures, so you climb the jointing, and if you get a basalt that's reasonably fresh and it's been covered, the material that's covered has percolated down to fill in all those fractures, you can have a potentially really, really good aquifer system. Okay, the Hawaiian Islands do. So there's a few values, okay, of porosity. You can see it's quite a range of stuff. And you can see the unconsolidated material or plastic material will have reasonably, or it has reasonably high porosity, certainly compared to some of these things here, which can go down to pretty much zip. Okay, nothing whatsoever if these rocks are really tight. So your cast limestone, that's only secondary porosity, fractured basalt, secondary porosity. Okay, you can get quite a high amount of porosity, 50%, so they can potentially hold a lot of water. Here's a clastic rock sitting on top of a fractured crystalline rock. Okay, this porous rock here, or regolith, 30% porosity. And here, this stuff here on average only 1%. You can see the big difference it has in the amount of water stored in the rock itself. Okay, there's a lot of water in here. 30% of that potentially is water. This here, only a tiny amount, only 1%. You can see it gets worse and worse as you go deeper and deeper and deeper, because of course, as you go deeper, fractures tend to close up or not form. Okay, in these things, so you can see quite a big difference in the potential for fractured rock to store water compared with the clastic rock or really porous and stuff. Not to say, like I say, that these aren't good aquifers. Fractured rock aquifers are great. Okay, potentially really, really good for a whole variety of reasons. Specific storage. Righty, so it can get a little bit more complicated here. The volume of water, okay, the unit volume, so unit 111, okay, it can be a metre by a metre by a metre, or foot by foot by foot, it doesn't matter. The unit volume that will be released from the aquifer when you disturb the aquifer due to the compressibility of the aquifer itself and the decompression of the water, okay, per unit decline in hydraulic head. So you get a metre by metre, drop the hydraulic head within that a metre, right, and the aquifer, assuming it's a confined one, will slightly shrink, okay, because the pore water pressure has been taken off it, okay, so it'll compress very slightly. That compression forces water out, okay. You also decompress the water slightly when you disturb it, pop, okay, and it helps it force itself out as well. It's also, for obvious reasons, called elastic storage, because you're disturbing the aquifer. The problem is with specific storage, once you've done that to an aquifer, once you've reduced it and it's produced its water through specific storage, then you can't get that back again because you can't re-inflate them. Right, that's what it is. Okay, just the first formula of the day. So just density, that's gravity, okay, compressibility, porosity, and compressibility of water. Okay, and you get these values from these equations down here. You don't have to worry about that. You're not going to be doing it. It just shows you where it comes from. And in fact, this value here you get from a completely different method, which I'll talk about much later. Okay, but do remember storativity and the fact that it's elastic storage, because later on one of the other parameters depends quite heavily on that one. Okay, specific yield, much more important. Volume of water that will drain by gravity this time, okay, for a unit drop in water table from the unit volume of an unconfined aquifer. So if you take an unconfined aquifer and chop out a metre by metre by metre of it, drop the water level 1 metre, the water that drains out of that under gravity, so naturally flows out of it, is the specific yield, okay? It's sometimes called the drainable porosity. The specific yield is the proper term for this thing. Only relative to unconfined aquifers, because confined aquifers don't drain, okay? They're always saturated. Well, you hope they are, because if you drain them, then you're really up shit creek, because you're not getting them back at all, the aquifer's just killed itself. The amount you get out will be much less than the effective porosity, okay? Less down much less for various reasons, which I'll talk about in a minute. And that's what specific yield is, the volume of water drained over the total volume of the material you've drained it from on the unit material. Okay? And there's a little graphic, so you take your, it's a metre by a metre, drop the water level a metre, and whatever drains out is your specific yield. So you see a nice high specific yield would be really good, okay? For an aquifer, if you get lots of water out of it. Lower specific yield, not so good, but it's not the only thing that defines the suitability of an aquifer or not. There's always some water retained, as I said before. Molecular attraction, okay, capillarity, stuff that gets sealed up in voids and water that can't be released, etc., etc., etc. Okay, and that's called specific retention. So the specific retention and the specific yield will equal your porosity. Okay, the specific yield is the important one here. A couple of leading on to the next slide. Fine grained sediments have lower specific yields, for reasons we'll talk about in a minute. Okay, because surface tension always acts on these things. Water is sticky, okay, and then you use it to wash off all the sticky stuff. So water itself is inherently quite sticky. Okay, it possesses a dipolar charge. Hopefully you know all this from whatever science you did in high school. You did it, I hope you did it. So it's attracted to other water molecules, okay, by cohesion. It's also attracted to surfaces, adhesion, okay. Surfaces are charged, which they often are, okay. So water will try and stick to those if you can. There you go, positive, negative, okay, so they stick to one or the other, and even on the surfaces that people make reasonably hydrophobic, you'll still get water beading and sticking to these things, okay. That's one of its wonderful properties. Causes capillary retention where it sticks to grains in an aquifer. Okay, so it's specific retention. Okay, it's caused by these properties. So here's a thin section, here's some soil grains, okay, yeah. Here's a void where the water's gone from, but here and here, okay, you've got water that's stuck, it ain't coming out. Right? You're not able to get it out, okay, because it's sticking in there, okay, that capillarity, and its dipolar charge, whatever, are holding it in place. You're not able to move it. Clays are another issue, right? Everyone, you think of clay as being impermeable, right? As being not very porous, okay? Clay is really porous. Clay is massive, can hold a massive amount of water, okay? Vast amount of water. Problem is, clays, sheet silicates, have large surface area. They're very fine grained, okay? So massive amount of internal surface area. They also have a net charge imbalance, i.e. they have a charge. So water sticks to them really well. They also have large spaces within the crystal structure. Being sheet silicates, large holes in here. Okay, those large spaces hold water really well, and they don't let it go. They don't like it. So all those things hold water within our clays. So the total porosity, of clays can be really, really high, but the effective porosity is generally minuscule. Okay, they don't like giving up their water. So materials, total has porosity there, specific yield, specific retention, clay, 50% porosity, okay, up to lots and lots of ability to hold water. Specific yield, 2, okay, so it's holding 48 of that back, it's not letting it go, okay, so clays are a really bad example of good specific yield. Other things are a lot better. The gravel's really good. They give up most of their water, they retain very little. Okay? The coarser grained material is, the less water it will retain. So gravel's great stuff. Okay? That's your specific yield. Another storativity. This is where I said before that equation we talked about doesn't become vitally important. Volume of water and aquifer releases from storage per unit surface area per unit decline in hydro head. So here's a unit, right? 1 by 1 by 1, you drop the water level in it, and the amount of water that it releases, it's storativity. It's also known as the storage coefficient. Depending which book you read, some books are older than others, they tend to change the terms, and they've been bandied around differently over time, but they're all the same thing. Behaves differently depending on you're dealing with a confined or an unconfined aquifer. In an unconfined aquifer, this term here, okay, so that's your specific storage, and B is aquifer thickness, that term is absolutely negligible. It contributes virtually nothing to the groundwater you're taking out of an unconfined aquifer. Remember that here is where the aquifer collapses a bit, squeezes water out of an unconfined aquifer. You're not getting very much of that, or its contribution is very small to the overall yield of the aquifer itself. Okay, and so in an unconfined aquifer, basically what you had before, the storativity is equal to your specific yield, that amount that you can drain out under gravity. Okay, so that makes it nice and easy. The confined aquifer, this term is irrelevant because of course you don't drain the aquifer under gravity, the aquifer stays saturated. So the only component of the storativity that's acting this time is your specific storage, that elastic component. Okay. So the water is released from storage by compression, the aquifer expansion of the water when pumped, specific storage. The full aquifer thickness contributes though, okay, and so you need to multiply your SS by B in metres to get the value of storativity for your aquifer. The storativity is one of those things we'll talk about again later. It's one of those parameters that we get through actually testing an aquifer out, putting a well into it, pumping it out, taking measurements using various graphs and equations to get that value. It's a very important value. You can see that, of course, if you have a really high storativity, okay, you're likely to be dealing with unconfined aquifer if you're not sure. If you have a very low storativity, you're likely to be dealing with, you're either really unlucky, or you're dealing with a confined aquifer, because this number here is generally very low, and this number here is generally very high. So there's the two combined, compared. Okay. So what you do is you drop the geometric surface, in this case it's the water table, by the unit values. In this case 1 metre, this 1 by 1 by 1 by 1. That's the water that comes out. Essentially this, remember, this first one here, it's drained, so it's equal to your specific yield. Here you can drop the geometric surface or the piezometric surface in your well by pumping whatever by a metre, but you can see here only get a little tiny drop in the surface itself, okay, in the real one, and you only get a tiny little bit of water coming out of there, okay, so that storativity is a very different thing depending on whether you're dealing with confined or unconfined aquifers, so just be aware of that as well. Okay, the effects of storage this time. We have the effect of, porosity. Okay, here I've taken an aquiclude, so we've got an aquifer down here that's confined, okay, with a very low storativity, 1 times 10 to the minus 4. Okay, so you see that kind of thing. In our results, we know we're dealing with a confined aquifer, and unconfined aquifer here, sitting on top, okay, filling up part of the regolith there, and a storativity of 0.2, so quite good, okay, quite porous material. Okay, so when you start wanting to take material out, you can see the vast differences in storage between the unconfined aquifer and the confined aquifer as well. And that, of course, has a lot to do with the amount of area that the water has to work with in there too. If you consider both of these aquifers, this one and this one, and recharging them, so somehow rainfall percolates down certainly through the ground into this one and somewhere else here, and you get the equivalent of a millimetre, okay, of rainfall percolating down to each aquifer. It has very different effects, okay, on both of those aquifers. Okay, so this one here, okay, it's going to raise the water table. This one here will raise the piezometric surface. I haven't got that on here, but it could be anywhere. Either way, it's going to have quite a marked effect. Those two surfaces are going to raise very different amounts because of the values of S here being very low and S here being very high. The unconfined aquifer, a millimetre of rain, 0.2 storativity, you get a 5 millimetre rise in the water table. So you can get a rise, okay, and it'll be 5 millimetres. Of course, this is much less very porous, okay, it's still in space to store water. It doesn't need to raise very high to accommodate that 1 millimetre of rainfall. The unconfined aquifer, it's quite a dramatic increase. Okay, it's 1 millimetre, 1 times 10 to the minus 4. You'll get a 10 metre rise in the piezometric surface. Okay, so that artificial water table, that pressure head above the aquifer, wherever it happens, will rise 10 metres. Of course, conversely, if you start pumping these things and you pump this thing to the equivalent of a millimetre of aquifer level gone, then you get a 10 metre drop as well. Okay, so you don't look at this and go, wow, a little tiny bit of water gives us a huge amount we can play with. It doesn't work like that, okay? The reverse also happens when you start disturbing these things, start burrowing into them and upsetting the balance, which is why it's really important to know the system that you're dealing with. And so the second the last 4 lectures of this part of the course. We'll do that in detail. All right, I might start on stuff as well. We'll make sure we get through it. Darcy's law. This is something that you hear bandied up all the time in hydrogeology. Okay, Darcy's law, Darcy this, Darcy that, whatever. Sort of the beginning. He was one of the first guys to actually actively start empirically studying groundwater, its flow of water through media, through porous media. They come up with a reasonably simple law, which is used a lot by everybody. It's applicable in certain situations, not so much in others. I'll point out some of them as we go, but overall, it's a very good thing. Anything to do with groundwater, textbook, you look it up on Google, whatever, it doesn't matter. You're going to encounter Darcy's law in one form or the other. He was a French engineer, and Paris wanted to make grubby water, and they wanted to filter the water through layers of sand, and he did a whole lot of experiments filling a pipe with various types of sand and pouring water through it and measuring the rate at which the water flowed through it, okay, trying to get some sort of quantifiable data from the experiments that they then applied to the water drainage system. So you set up an apparatus and something like this. Here's the sand packed here in this tube. 2 manometers coming out of it, one low down in the tube, one high up in the tube, and they're a distance apart L. Okay, and when you fill this up with water and you supply water through the tube at a constant rate. Okay, it comes out the bottom. Okay, at a constant rate. And the water levels in the 2 manometers will rise to different levels. The one higher up, one at higher pressure, so it rises to a greater height. The one lower down to a lower height. Okay, and so you've got H1, H2, and the difference between them there. Okay, those are important. The water goes in at a constant rate. Okay, it comes down at a constant rate. Okay, that's the discharge or the recharge, Q. Okay, so we're going to begin with Q and L, and we're going to begin with H1 and H2. Okay, there's another variable that pops in here as well, which is a really important one. So anyway, he was just playing around, and in his experiments he discovered that the flow or discharge, okay, with the amount coming out here, is proportional to the area of the pipe. Of course it is. Okay, it just makes sense. It's also proportional to the height difference of water at the top and the bottom, so the difference in hydraulic head between the top of the pipe and the bottom of the pipe. Okay? Inversely proportional to the distance the 2 measuring pipes are apart. Okay? And so he came up with this equation here, K A H1 minus H2 over L equals Q. So discharge is the area times the hydraulic gradient, that's what that thing is there, difference in height over difference in between the 2 measuring points. And this value here, K, is a really wonderful little value called hydraulic conductivity. Okay, that's how we write it normally, the HDL, so difference in difference in length, difference in heat, difference in length. There's a negative there because the water is flowing down gradient, downhill. Okay, that negative will just disappear, it sort of comes and goes as people please, it doesn't matter. Essentially the equation is Q equals K, in this case A dHdL. This here is replaced by a single term I, hydraulic gradient. So essentially the equation you'll see it later on when I show you is Q equals KIA. So it is A there. It's negative because water flows from high pressure to low pressure. If you're pressurizing and forcing the water to flow uphill, it'll be positive. It doesn't matter. Okay, it's a semantic. It's not going to worry anything that we do in the course. K is a coefficient, hydraulic conductivity. It can be determined through various means, very pokery, either experimental or doing stuff which we'll talk about later, later in the course. That's Darcy's law in a nutshell. That's what it is. It's this thing here. Okay? Q equals KIA. It's very important. You see it used and moved around in various forms. In the rest of this lecture, and certainly in the stuff I talk about later on when we start developing wells, getting water out of it. So what is this thing called hydraulic conductivity? It's a rate. Remember, we're into flow properties now. We've done storage properties, now we're into flow properties. So it's a rate, it's a velocity. The rate of flow through a unit cross-sectional area of media, so area 1 by 1, okay, under a gradient of 1. So that means for every metre you move horizontally, you move 1 vertically. So essentially you've got an area of material like this, and you have water going through it at a gradient of 1. That's what it means. Okay, it's